There is a kind of ice at the bottom of the ocean that burns. Hold a piece of it in your hand and it hisses and fizzes, and if you touch a flame to it, the ice itself catches fire, a lump of frozen water, wrapped around a heart of trapped gas, burning in your palm while it melts. There is more of this burning ice buried under the seafloor than all the coal, oil, and natural gas on Earth combined. It is called methane hydrate. It is one of the largest stores of carbon anywhere on the planet. It has been building up on the ocean floor for millions of years, and this is the part that matters, it is not stable. It is held together by nothing but cold and pressure, and both of those can change. In 2014, in the frozen north of Siberia, a crater appeared overnight, a perfectly round hole, 30 meters across, blasted into the tundra with such force that chunks of earth were thrown hundreds of meters. There was no meteorite. There was no bomb. No one had drilled there, and no one had set a charge. The ground had simply, violently exploded, from below, and entirely on its own. And for decades, one of the great mysteries of the sea has been ships that vanish without a trace, in calm water, with no wreckage and no distress call. One explanation, argued by serious scientists, is that the ocean itself can open up beneath a vessel and swallow it whole. All of these things, the burning ice, the exploding tundra, the vanishing ships, are connected by a single substance. A gas that is frozen into the floor of the ocean and the soil of the Arctic in almost unimaginable quantities. A gas that is mostly harmless when it stays put, and catastrophic when it does not. And the reason scientists are afraid of it is written into the planet's own past. Because the single worst day in the history of life on Earth, a die-off that nearly ended everything, may have started exactly this way. With the ocean catching fire. We will get to all of it, the exploding tundra, the ships, the ancient wave that drowned a country, and the day the planet nearly died. There is footage, if you go looking, of scientists doing the impossible seeming trick, holding a lump of this hydrate in a gloved hand and setting it alight. The flame dances on the surface while water drips from the bottom. Fire and ice, in the same fist, at the same moment. It looks like a magic trick. It is instead one of the most consequential substances on the planet, and almost nobody outside of science has heard its name. But first you have to understand this strange substance itself, what it actually is, where it hides, how much of it there is, and why the ground beneath the sea is, in places, a loaded gun waiting for the temperature to pull the trigger. Go down to the seafloor, a few hundred meters or more beneath the surface, where the water is near freezing and the pressure is immense. Here, in the cold and the dark, water and methane gas do something they cannot do anywhere in your daily life. They lock together into a solid. The water molecules form a microscopic cage, a lattice of ice, and inside each cage sits a single molecule of methane, trapped. The result looks like ordinary dirty ice. But it is not ordinary at all. It is a substance that only exists in a narrow band of cold and high pressure, and it holds an astonishing amount of gas. Melt 1 cubic meter of methane hydrate, and it releases around 160 cubic meters of methane gas. The ice is a compression device, squeezing an enormous volume of flammable gas into a small block of what looks like frost. That is why it burns in your hand. The flame melts the cage, the methane rushes out, and it ignites. Think about what that compression means. A small chunk of this stuff, no bigger than a snowball, holds enough natural gas to fill a large beach ball. A deposit the size of a swimming pool holds enough to heat a town. And the ratio works in reverse, too, which is exactly the danger. When it melts, that snowball does not become a puddle. It becomes a beach ball's worth of gas, expanding violently, forcing its way out of the seabed with enormous pressure behind it. For a long time, we did not even know it existed in nature. Methane hydrate was first noticed as a nuisance, a mysterious ice that kept clogging natural gas pipelines in cold climates in the 1930s, forming plugs where liquid water should have stayed liquid. It took decades before geologists realized the same substance was forming naturally, on a colossal scale, across the floor of every ocean on Earth. A pipeline headache turned out to be one of the largest carbon reservoirs on the planet. Now multiply that block by the entire floor of the world's oceans. Methane hydrate forms in a layer beneath the seabed all around the planet, along the edges of the continents, in the Arctic, anywhere the cold and pressure are right. The total amount is staggering. The most cited estimates put the carbon locked in these hydrates at more than all the world's other fossil fuels put together. And it is not only in the ocean. Across the Arctic, the same frozen gas is locked into the permafrost, the permanently frozen ground of Siberia, Alaska, and northern Canada. For tens of thousands of years, the cold has kept it sealed. A vast, invisible reservoir of flammable gas, held in place by nothing but temperature. And the permafrost holds a double threat. It is not only leaking preformed methane, it is also packed with the frozen remains of ancient plants and animals, carbon that has been locked in the freezer for tens of thousands of years. As the ground thaws, microbes wake up and begin to feast on that ancient organic matter, and as they digest it, they produce fresh methane and carbon dioxide of their own. The Arctic soil is both a gas tank and a compost heap, and warming switches both of them on at once. The scale of what is frozen up there is hard to grasp. The world's permafrost is estimated to hold roughly twice as much carbon as is currently in the entire atmosphere. It is one of the largest carbon stores on the planet, built up over ice ages, and for all of human history it has simply sat there, frozen and silent. We are now, for the first time, watching the freezer door swing slowly open. And here is the problem that keeps scientists awake. The thing holding all of it in place, the cold, is exactly the thing that is now changing. Warm the water, or warm the ground, even a little, and the cages begin to open. The ice that burns begins to melt. And when it melts, it does not do so quietly. Nowhere has that been clearer than in the far north of Siberia, where the ground has started, without warning, to blow itself apart. The Yamal Peninsula juts into the Arctic Ocean in northern Siberia. Its name, in the language of the native Nenets people, means roughly the end of the world. It is a flat, frozen, treeless expanse of tundra, dotted with reindeer herders and, more recently, some of the largest natural gas fields on the planet. In the summer of 2014, a helicopter crew flying over the tundra spotted something that should not have been there. A hole. Enormous, dark, and almost perfectly circular, punched into the flat ground with a raised rim of ejected earth around it, like the mouth of a small volcano. When scientists reached it, they found the signs of an explosion. Frozen chunks of soil and ice had been hurled up to hundreds of meters away. The hole was tens of meters wide and plunged deep into the permafrost, with water pooling at the bottom. Something had detonated here, but from underneath. Getting real answers meant going in. Researchers actually rappelled down into these craters, lowering themselves on ropes into a freshly blasted, unstable hole in thawing ground, not knowing whether more gas might still be building below them. Down in the shaft, instruments measured the air, and the readings confirmed it. Methane concentrations near the bottom were far above normal, in some cases high enough to be explosive. They were standing inside the barrel of a gun that had just gone off. And the most chilling detail came later, when scientists learned to spot them before they blew. In the years since, researchers have identified mounds on the tundra that bulge upward, the ground visibly doming as gas accumulates beneath it, sometimes by several meters. These are craters waiting to happen. Fly over parts of the Yamal today and you can see the blisters on the skin of the Earth, swelling, each one a future explosion on a timer no one can read. The explanation that emerged is unsettling in its simplicity. As the Arctic warms, the permafrost thaws from within. Pockets of methane, some released from melting hydrates, some produced by microbes waking in the warming soil, build up in a cavity underground. The pressure rises. The frozen lid of soil above holds it in, like a cork in a shaken bottle. Until it doesn't. When the pressure exceeds what the weakening ground can hold, the whole thing bursts, blasting soil, ice, and gas into the sky, and leaving behind a clean, round crater. The Nenets herders reported that some were preceded by a flash of light and a bang. The end of the world, living up to its name. Since that first discovery, more of these craters have been found across the Siberian Arctic. Each one is a small, local demonstration of the same principle: trapped methane, a warming climate, and a ground that can no longer hold its breath. They are dramatic. They are strange. And they are, scientists fear, the smallest version of a much larger problem. And they do not stay as craters for long. Within a few years, each explosion hole fills with meltwater and becomes an ordinary-looking Arctic lake, indistinguishable from the thousands already dotting the tundra. Which raises an unsettling question the scientists asked immediately: how many of the lakes already scattered across Siberia are old craters, from blasts nobody was there to see? The evidence of past explosions may be hiding in plain sight, disguised as scenery. There is a very practical fear here too. The Yamal Peninsula is not empty, it holds some of the largest natural gas operations on Earth, threaded with pipelines, roads, and settlements. A crater like these, opening under a pipeline or a building, would be a disaster. The Russian scientists studying them are not only chasing a scientific curiosity. They are trying to predict where the ground will next blow open beneath critical infrastructure. Because the same gas, in far greater quantities, is buried under the sea. And the ocean has its own way of letting it out. For centuries, sailors have told stories of ships lost in calm seas. No storm. No collision. No wreckage washed ashore. A vessel simply gone, as if the ocean had opened a mouth and closed it again. Most of these stories are just the ordinary cruelty of the sea, storms that came and went, hulls that failed far from any witness. But one explanation, for some of them, comes straight from the burning ice below. Sailors have always known certain patches of water to be unlucky. Long before anyone understood methane, there were sea legends of water that would not hold a ship up, of vessels that sat strangely low, of sudden losses in weather that should have been survivable. We tend to dismiss these as superstition. But buried inside some of them may be a real observation, passed down without an explanation, that the sea, in certain places, can betray the fundamental promise it makes to everything that floats. Imagine a pocket of methane hydrate on the seabed destabilizing all at once, a slope of it collapsing, or a reservoir of gas breaking free. A vast volume of methane rushes up through the water as a great cloud of bubbles, a column of froth rising toward the surface. And here is the physics that dooms a ship caught above it. A vessel floats because the dense water beneath it pushes up. But water full of gas bubbles is not dense, it is a froth, far lighter than solid water. If a ship suddenly finds itself floating on a churning column of bubbles instead of water, it loses its buoyancy in an instant. It does not sink slowly. It drops, like a stone, straight down. You can feel a tiny version of this yourself. In a jacuzzi or a heavily aerated pool, a body floats noticeably worse, the bubbles thin the water. Now scale that up to a supertanker and a column of methane hundreds of meters wide erupting beneath it. There is nothing the crew could do. No alarm, no maneuver, no time. The water simply stops being water, and the ship falls through it into the deep, its own way closing over it in seconds. And there is a second act to the horror, because methane is flammable. If that rising gas reaches the surface around a ship and finds a spark, an engine, an exhaust, an electrical fault, the sea around the vessel can literally catch fire. Sailors' oldest nightmare made real, not just the ocean opening up to swallow you, but the surface of the water itself bursting into flame as it does. The day the ocean caught fire, in the most literal sense. This idea has been attached, inevitably, to the Bermuda Triangle, the stretch of the western Atlantic where ships and planes have supposedly vanished in unusual numbers. Some scientists proposed that methane eruptions from the seafloor could explain sudden sinkings there. It is a genuinely debated hypothesis, and an appealing one. Researchers have actually tested it. In laboratory tanks, they released bubbles beneath model ships, and watched the models lose buoyancy and sink the moment the frothing water reached them. The mechanism is real. A ship above a large enough methane release genuinely could go down without warning, without a storm, without a trace. There is even a version of this fear for aircraft. Methane rising and reaching the air is lighter than normal atmosphere and highly flammable. In principle, a large plume drifting up around a low-flying plane could disturb its instruments or, in the worst case, ignite. It is far more speculative than the ship scenario, and there is no solid proof it has ever downed an aircraft. But it is one more reason the burning ice attached itself so firmly to the legends of the Bermuda Triangle, where both ships and planes were said to vanish. Now the honest part, because we deliver on every promise. The evidence that this has actually sunk real ships in the Bermuda Triangle is thin. Studies of that region have not found the huge, recent hydrate blowouts the theory would require, and the triangle's disappearance rate may not even be unusual. So treat the Bermuda link as a maybe, not a fact. But the underlying phenomenon is not a maybe. Off the coast of Norway, scientists have mapped a giant crater on the seafloor called the Storegga area, where the seabed is pockmarked with the scars of ancient methane blowouts, holes hundreds of meters wide, blasted out of the ocean floor by escaping gas. The sea has swallowed things before. We have the craters to prove it. These scars have a name: epoch marks. Sonar surveys of the world's continental shelves have revealed them in staggering numbers, fields of craters, some the size of stadiums, pitting the seabed across entire regions. Each one marks a place where gas once forced its way violently out of the ground. Off Norway alone there are pockmarks big enough to swallow buildings. The floor of the ocean is, in places, a battlefield of old explosions we never saw and never heard. One of them, off the Norwegian coast, is so large it has its own name, a pockmark hundreds of meters across and tens of meters deep, gouged out of the seabed in a single ancient blast of methane. Stand at its rim in a submersible and it looks like a bomb crater on the moon. It is a monument to the fact that the burning ice does not always leak politely. Sometimes it detonates. And one of those ancient collapses did far more than sink a ship. It sent a wall of water across an entire sea. 8,000 years ago, the North Sea was different. Britain was not yet an island. It was joined to mainland Europe by a low, marshy plain that archaeologists now call Doggerland, a lost country of rivers, forests, and hunting grounds, home to Stone Age people who lived and fished across what is now open sea. Off the coast of Norway, at the edge of the continental shelf, an enormous slope of seabed sediment had built up over thousands of years, and it was riddled with methane hydrate. Something triggered it, an earthquake, the pressure of the ice ages lifting, or the hydrates themselves destabilizing. And the whole slope let go. It is called the Storegga Slide, and it is one of the largest known landslides on Earth. A volume of sediment big enough to bury a large country under many meters of debris slid off the continental shelf and thundered into the deep Atlantic. And when that much material moves that fast underwater, it shoves the ocean aside. The numbers are hard to hold in your head. The Storegga Slide moved a volume of material estimated in the thousands of cubic kilometers. The debris field runs for hundreds of kilometers across the sea floor. It is as if a chunk of a continent had simply detached and slid into the abyss. And it was not a slow creep over centuries. Once it started, the collapse would have raced downslope in hours, a catastrophe unfolding at the speed of an avalanche. Here is why hydrates are the prime suspect. Methane hydrate acts like a glue and a scaffold inside seabed sediments, helping hold the slope together. Warm the water even slightly, and the hydrate melts, turning solid, stable sediment into a weak, gassy sludge, primed to slide. Many of the largest underwater landslides in the geological record sit exactly where hydrates would have been destabilizing at the time. The burning ice does not just explode. It can pull the very ground out from under the sea. The result was a tsunami. A wall of water that raced outward across the North Sea and slammed into the coastlines around it. In the Shetland Islands, the deposits it left behind sit 20 meters above the old sea level. It swept across Doggerland, drowning the low plain, and helped finish the process that turned Britain into an island. We know this happened because the wave signed its name in the ground. All around the North Sea, geologists find a distinctive layer of sand, sediment ripped from the seabed and flung far inland, sitting incongruously in the middle of ancient peat and soil. That single grey band, traceable across hundreds of kilometers of coastline, is the fingerprint of one afternoon 8,000 years ago. Wherever it appears, the Storegga wave reached. For the Stone Age people living on that coast, it would have been apocalyptic and utterly without warning, the sea drawing back, then returning as a mountain of water. We will never know how many died. An entire inhabited landscape was erased from the map in an afternoon, and the survivors, cut off, watched their world become the seabed. Doggerland has not vanished entirely. Fishing trawlers dragging the floor of the North Sea still haul up its remains, the bones of mammoths and ancient deer, and work tools of stone and bone, snagged in nets from a drowned country. Museums now hold artifacts fished out of the sea that were made by people walking on dry land where waves now roll. The Storegga tsunami helped seal that world away, and the ocean occasionally, grudgingly, hands a piece of it back. The reason this ancient wave matters now is that the conditions that made it are not extinct. There are steep, hydrate-laden slopes off many of the world's coastlines today. Warm the water enough, and one of them could let go, just as Storegga did, except now the coastlines it would strike are crowded with cities, ports, and millions of people. Submarine landslides remain one of the most underappreciated tsunami risks on the planet, and the burning ice is one of the triggers scientists watch for. The exact role of methane hydrate in triggering Storegga is still debated. The melting ice sheets and earthquakes of the era were involved too. But hydrates are a leading suspect, and the lesson is clear: the frozen gas in the seabed is not just a source of local explosions. Destabilize enough of it, on a steep enough slope, and it can move the ocean itself. And if that sounds like the worst the burning ice can do, it isn't. To find the true nightmare, we have to go back not 8,000 years, but 250 million. 252 million years ago, long before the dinosaurs, life on Earth came closer to ending completely than at any other moment in its history. Scientists call it the Permian-Triassic extinction. Most people have never heard of it. Its nickname says everything: the Great Dying. When it was over, roughly 90% of all species in the ocean were gone. On land, perhaps 70% of vertebrate species vanished. Forests collapsed. Even insects, which almost never suffer mass extinctions, were devastated. Life on Earth was reduced to a fraction of what it had been, and it took millions of years to recover. To put that in perspective, the asteroid that killed the dinosaurs, the most famous extinction of all, wiped out around 3/4 of species. The Great Dying was worse, the closest the planet has ever come to sterilizing itself. If it had gone just a little further, complex life might have been erased entirely, and the Earth returned to a world of nothing but microbes. Everything that came after, the dinosaurs, the mammals, the forests, us, exists only because a thin remnant of life scraped through that eye of the needle. What caused it? The trigger was almost certainly volcanic, not a single volcano, but a colossal outpouring of lava in what is now Siberia, erupting across an area the size of a continent for hundreds of thousands of years. But volcanoes alone may not explain the sheer scale of the catastrophe. And this is where the burning ice comes back into the story. Because those Siberian eruptions did not happen in an empty landscape. They tore through vast deposits of coal, oil, and, crucially, methane. The heat is thought to have cooked enormous quantities of methane and carbon dioxide out of the ground and the seabed, releasing them into the atmosphere and oceans in a runaway surge. Picture the mechanism. Rising magma did not just erupt at the surface, it forced its way sideways through the buried carbon deposits, baking them like an oven. Coal beds, petroleum, and frozen gas superheated all at once across an area the size of a continent, for millennia. It was as if someone had lit the planet's entire fossil fuel reserve, slowly, from below. The carbon that took hundreds of millions of years to bury came roaring back into the sky in a geological instant. The chemical fingerprints are still readable in the rocks. Scientists find a sharp, massive shift in carbon signatures at exactly the extinction layer, the signature of a colossal injection of light carbon, the kind that comes from methane and fossil deposits, dumped into the system faster than the planet could absorb it. The rocks recorded the crime. It took us 250 million years to read the confession. And methane is a monster of a greenhouse gas, far more powerful, ton for ton, than carbon dioxide over the short term. Here is the nightmare scenario scientists call the runaway feedback. Warming from the volcanoes and the first gas release warms the oceans. Warmer oceans destabilize their methane hydrates, which release more methane, which causes more warming, which melts more hydrate. A vicious circle, feeding on itself, spiraling out of control. The oceans heated up and acidified. Oxygen drained out of the water, leaving vast dead zones where nothing could breathe. On land, the temperature soared. It became, quite literally, a planet trying to kill everything on it, and very nearly succeeding. The fossil record of that moment is a layer of near emptiness, the closest life has ever come to the end. Consider one detail that captures the horror. Near the equator, the sea surface may have reached around 40 degrees Celsius, bath water, stretching across the tropics. It was so hot that fish and marine reptiles seemed to have abandoned the equatorial seas entirely. The tropics became a dead zone that life fled. A world where the ocean is too warm to live in is not science fiction. It is a chapter of Earth's actual history, and the burning ice helped write it. And the sea did not just empty, it turned strange and poisonous. As oxygen vanished, the oceans came to be dominated by bacteria that produce hydrogen sulfide, the same rotten egg poison of the deep vents, but now on a planetary scale. Some scientists think this toxic gas bubbled up out of the sea and into the air, killing on land as well. For a while, the Earth may have smelled of rotten eggs from pole to pole, the exhaust of a dying biosphere. Life did survive, barely. A handful of hardy species crawled through the bottleneck and, over millions of years, repopulated the world. The dinosaurs would eventually rise from the ashes of that recovery. But the Great Dying stands as a permanent warning, written in stone. This is what can happen when the planet's carbon, including its frozen methane, is released too fast. And the Permian was not the only time. Around 56 million years ago, long after the dinosaurs were gone, the Earth went through a sudden, sharp warming event, smaller than the Great Dying, but eerily instructive. Scientists studying it find, once again, a massive burst of light carbon flooding the system, and methane hydrates are a prime suspect for where much of it came from. The planet warmed several degrees, the oceans acidified, and species reshuffled dramatically. It was, in effect, a dress rehearsal or a milder run of the same experiment. The detail that unnerves climate scientists is the speed. Those ancient carbon releases, terrifying as they were, mostly unfolded over thousands of years. Human beings are now releasing carbon into the atmosphere faster than at almost any point in the geological record, faster, quite possibly, than even the event that helped drive the Great Dying. We are not just repeating an old experiment. We may be running it at a speed the planet has rarely, if ever, seen. And that warning is not just about the distant past. Because the conditions that unlocked the burning ice back then are, in one specific way, being recreated right now. The Arctic is warming faster than almost anywhere else on Earth, several times faster than the global average. And the Arctic is exactly where the most vulnerable methane is stored, in shallow seabeds and thawing permafrost, held in place by a cold that is now slipping away. In the shallow seas off the Siberian coast, scientists have found columns of methane bubbling up from the seafloor, plumes of gas rising through the water, some reaching the surface. Researchers have described areas where the sea appears to be, in their words, boiling with escaping gas. The frozen lid is leaking. The expeditions that found these plumes describe something genuinely eerie. In the East Siberian Arctic Shelf, the largest and shallowest continental shelf in the world, teams have sailed over patches of sea hundreds of meters across where the water fizzes continuously, methane streaming up in curtains of bubbles thick enough to show up on the ship's sonar as ghostly columns rising from the dark. Some of these seep fields have grown year over year, as the water warms. And the shallowness is what makes this region the one scientists worry about most. In the deep ocean, methane rising from the floor has kilometers of water to travel through, and most of it dissolves or gets eaten by bacteria before it ever reaches the air. But on a shallow shelf, only tens of meters deep, the gas has almost no distance to cover. It can punch straight through to the atmosphere, bypassing the ocean's natural filter. This is the one place the burning ice has a clear path to the sky. Now, the crucial honest context, because fear without accuracy is just noise. Scientists disagree, sharply, about how dangerous this is. Some warn of a possible methane bomb, a large, sudden release that could accelerate warming abruptly. Others argue the deep ocean hydrates are far more stable than the alarming headlines suggest, and that any release will be slow, over centuries, not years, giving the gas time to break down in the water before it ever reaches the sky. There is real comfort in that second view. Most methane released underwater is consumed by bacteria or dissolves before it surfaces. The deep hydrates are buried under pressure and sediment that resist rapid change. A sudden, planet-wrecking belch, most scientists agree, is unlikely on any human timescale. But unlikely to be sudden is not the same as safe. Even a slow, steady leak of methane from a warming Arctic adds to the warming that is causing the leak in the first place, a gentler version of the same feedback loop that helped drive the Great Dying. It does not need to be an explosion to be dangerous. It only needs to be a nudge, in the wrong direction, that keeps nudging. That is why scientists watch the burning ice so closely. Not because the ocean is about to erupt into flame tomorrow, but because we are running, in slow motion, a smaller version of an experiment the planet has already run once before, and we know how that one ended. There is one final irony worth sitting with. This same substance, the ice that burns, is also seen as a potential fuel. Nations have spent fortunes trying to mine methane hydrate from the seabed for energy. The very thing that may have nearly ended life is also one of the largest untapped energy reserves on the planet. Fire and catastrophe, frozen into the same block of ice. Japan, a country with almost no fossil fuels of its own, has led the charge, successfully pulling natural gas from seabed hydrates in test operations off its coast. China has done it too, hailing it as a strategic breakthrough. The prize is enormous. A single nation's hydrate deposits could, in theory, hold centuries of energy. It is the largest fossil fuel reserve humanity has never touched, sitting on the ocean floor, waiting. But mining it is like defusing a bomb by pulling on its wires. Disturb a hydrate deposit carelessly and you risk the very thing this whole story is about: destabilizing the seabed, triggering a slide, releasing an uncontrolled surge of the most potent greenhouse gas there is. We are contemplating harvesting, for fuel, the same substance whose sudden release may have nearly ended life on Earth. It is either the energy source of the future or the fuse of a catastrophe, and it is the exact same block of ice. So the next time you picture the ocean, add this to the image. Beneath the waves, under the cold seabed, sleeps a giant made of frozen fire, more carbon than all our coal and oil, held in place by nothing but temperature. For now, it sleeps. It has slept, mostly, for millions of years. Step back and the whole story becomes a single, simple pattern that has repeated across deep time. The planet keeps enormous amounts of carbon locked away, in rock, in ice, in the frozen seabed. Most of the time it stays put, and life flourishes in the calm. But every so often, something unlocks it too fast: a supervolcano, a warming pulse, a slope collapse. The carbon floods out, the world heats, the ocean sour, and life pays the price. Then, over millions of years, the planet slowly buries its carbon again, and the cycle resets. What is new, this time, is us. For the first time in the planet's history, the thing unlocking the carbon is not a volcano or a wobble in Earth's orbit. It is a species, digging up buried carbon and burning it, and warming the very Arctic that holds the frozen rest. We have, without quite meaning to, appointed ourselves the trigger. The burning ice does not know we exist. But it will answer to the warmth we make, exactly as it always has. Whether it keeps sleeping depends, in part, on us. The burning ice does not care about human beings. It only obeys the cold. And the cold, at the top of the world, is quietly, steadily, giving way. It is worth being chloride rather than fearful. The most likely future is not a Hollywood explosion, not the ocean bursting into a wall of flame overnight. It is something slower and, in its way, more insidious, a steady exhale of methane from a warming Arctic, adding its weight to the warming we are already causing, nudging the feedback loop along by degrees. The giant probably will not wake with a roar. The worry is that it is already stirring in its sleep. This is why, right now, there are instruments scattered across the Arctic seabed and tundra, listening. Buoys measuring the methane in the water. Towers sampling the air. Satellites watching the plumes from space. We have become a civilization that keeps a nervous watch on a substance most people have never heard of, because we finally understand what it did once before, and what it could do again. Remember the burning ice. Remember that the calm surface of the sea rests on a foundation of frozen fire, and that the whole arrangement is held together by nothing more than cold. It is one of the quiet, invisible bargains the planet has always kept, and one we are, without fully meaning to, beginning to renegotiate. If this journey changed the way you think about the ground beneath the sea, stay with us. The next descent goes to the place where the ocean floor is not sleeping at all, where the seabed itself is being pulled down and destroyed, and an entire ocean is slowly disappearing.